So in the second vodcast about solubility equilibria, we're going to look at the common ion effect and how you can quantify the solubility of a salt when you add a common ion to it. So for example, if this is barium sulfate, sparingly soluble dissolves into barium and sulfate ions. If I might add some barium chloride or some sodium sulfate, the effect of adding barium ions or adding additional sulfate ions will shift my equilibrium back to the left and will result in a greater pile of solid stuff appearing at the bottom of my beaker as I drive the equilibrium to the left, making the barium sulfate less soluble by the addition of ions in common. Now let's do a specific problem with that, and that problem would be sample exercise 17.12. Let's assume that we have a solution that's already got 0.01 molar in calcium nitrate. And you want to calculate what would happen to the solubility of calcium fluoride if you were to add it to that solution. To me, I kind of look at it from the opposite direction, but I'll go with the way that this problem solves it. So we need to find the molar solubility of calcium fluoride. That means you need to write the calcium fluoride equation showing dissociation and solubility expression. And then you'll need to go to the chart of solubility products and find the KSP. So we start off with a solution that is 0.01 molar in calcium ions because you had calcium nitrate. You don't have any fluoride ions just yet because we haven't actually added the calcium fluoride. Now we add the calcium fluoride. Well, when you add the calcium fluoride, that means you'll be adding X amount of calcium ions and twice that amount of fluoride ions. So the equilibrium amounts or concentrations will be 0.01 plus X, and that would be 2X. I substitute those values into this expression, 0.01 plus X times 2X squared, and that should be set equal to the KSP. Now at first that looks a little spooky, but what you get to do is this. You get to do that thing like we did in buffers and titrations. You get to ignore the X. So when you ignore the X, it cleans up quite nicely. 3.9 times 10 to the minus 11 equals 0.01 times 2x squared. Don't do like I do. Call that 4x squared. I hope they did that. And then I need you to solve for x, which involves at the end of this particular problem using your square root. How come you could make the assumption to ignore that x in this expression? Because the solubility of calcium fluoride is already really small. So when you add this 0.01 molar of calcium from the calcium nitrate, it's going to be very much greater than the solubility and the additional concentration that would come from the calcium fluoride. Essentially, you get to ignore the X. So when we solve for X, I want to double check and make sure I know what the question was. I solve for X, which stood for, in this particular case, the concentration of the calcium ion. And since there's one calcium from one calcium fluoride, I can assume that my final answer for X, the calcium ion concentration, is the same as the solubility of calcium fluoride itself, 3.1 times 10 to the minus 5 molar. So I'll say that again. Oftentimes you find the solubility of one ion, then you have to look at the solubility of that ion relative to its original solid salt. And since it's in a 1-to-1 ratio, the solubility of that calcium ion is the same as the amount of calcium fluoride that would have dissolved. Again, a very tiny amount, 0.000031. Okay? So that's how much would dissolve per liter of an already existing calcium nitrate solution. And that's because the calcium nitrate had an ion in common, the calcium, with the calcium fluoride. In the second question, I'm going to go back and refresh my memory. We apparently have 0.01 molar sodium fluoride. This time the common ion is going to be the fluoride ion. So we're asking what would be the solubility of calcium fluoride if we put it into a solution that's already got some fluoride ions in it, 0.01. So we go ahead and we write our same KSP expression that we'd had before, which was, and again you get to omit the X, the KSP will be equal to the calcium ion concentration times the fluoride ion concentration. You could do an equilibrium chart, but this is our, where'd that guy go? Oh, here's our concentration of the fluoride ion, 0.01. And why is it squared? Because there's 2 fluorides for every 1 calcium. This time, the fluoride ion will be increasing in concentration as well by the amount of, and they didn't draw an ice chart, so it's a little hard to see, by the amount of twice X. So if X stands for the calcium ion concentration, fluoride would equal 0.01, the original, plus the change, 2X, but go ahead and eliminate the X. So the KSP of calcium fluoride should be equal to X times 0.01 squared. Solving for X, you get 3.9 times 10 to the minus 7. And again, the calcium ion concentration, the 3.9 times 10 to the minus 7, is equal to the solubility of calcium fluoride per liter of that already existing sodium fluoride solution. So these problems are a little bit more challenging, but the math becomes simplistic. Don't forget about doing things like squaring as well as doubling X's, and making sure you do things like taking the square or sometimes the cube root of X at the end. Now the next kind of problem is what I call, will a precipitate form? And if you are doing one of these type of problems, it kind of goes back to that Q and KEQ thing. What we're going to do is we're going to calculate the reaction quotient given the problem, given the concentrations that were given in the problem. We're going to compare our Q, our pretend KEQ, to the KSP. And if it's equal to the KSP, it's at equilibrium, it's saturated. If your Q is less than the KSP, it means you haven't hit equilibrium yet. You could put in more solute and it would dissolve. And if the Q is greater than the KSP, that means that you've gone beyond the KEQ or beyond the equilibrium, and you're going to have salt precipitating out. So the questions always are like, will a precipitate form? Let's do one of those problems. They're going to take 0.1 liters of 8 times 10 to the minus 3 molar lead nitrate and add it to 0.4 liters of 5.0 times 10 to the minus 3 molar sodium sulfate. Now first you're going, wait, I don't get this. Here's what we're asking about. What would the precipitate be that could potentially form? You know to ignore nitrates and sodiums. So the only potential precipitate would be lead sulfate. And as soon as you identify that, you write an equilibrium expression, which of course they don't have here, but I would have done that. PbSO4 could split up into Pb ions or lead ions and sulfate ions. So that's the only product that you could potentially get. Once you know that it's PbSO4, that's the potential precipitate, focus only on the lead and sulfate ion concentrations and go trot to an appendix and get the KSP of lead sulfate. Now you also know when you add 2 volumes together, you're going to have a new total volume. So remember, we learned about that first dilute, then newt. Well, there's no newt in this one, but you definitely have to find the moles of your lead ion divided by the new total volume, and the moles of your sulfate, your sodium ion, no, your sulfate ions divided by the new total volume. So right here, volume times molarity gives me moles of lead, and lead moles divided by the new volume, because it was 0.1 liter plus 0.4, gives me the new concentration of my lead. Do the same thing for the 0.4 liters of sodium sulfate times its molarity, and you'll get its moles. Divide the moles by the new total volume, half of a liter or 500 milliliters, to get the new molarity of the sulfate. So now you have the 2 values you need to find the Q. This one's simple because it's a 1-to-1 ratio. lead sulfate turns into lead and sulfate. So there's no coefficients and no powers. So I simply substitute into my Q expression, which is the same as the KSP expression, except I use the given values. I get 6.4 times 10 to the minus 6. The last step is easy. You compare your calculated Q to the KSP. Our Q is greater than the KSP, which is 6.3 times 10 to the negative 7. That means, yes, a precipitate would have formed. And we're going to stop there to talk about in the next podcast the factors that affect solubility, specifically pH. But I'd like to draw your attention to now, you have a couple of more problems that you'll be able to do. Once again, this was on the solubility and KSP problems. This was sample exercise 17.13. But on the worksheet that says predicting precipitation, you will see another problem about will a precipitate form, as well as additional questions on KSP and solubility. In addition to these practice worksheets, remember you have calculations involving solubility products, a multiple choice worksheet, and 2 free response questions. And if any of those worksheets have will a precipitate form type of problems, please go to solve those as well. Take care.